and then the open circle makes the P for white power. So, and just so, and you know that symbol means like bad things in other countries too, right?
Oh, really?
Yeah, it's like putting the middle finger up in other countries. I don't know which countries those are, but I know I've definitely heard that. So, anyways, just looking out for you all. We'll go flashing the OK sign. Are there any questions over the homework?
Can you go over 8.3 number 9, I think?
Hopefully it's not. Okay, yeah, we'll talk about cotangents and cosecants at the end. We don't actually have any examples, but once we see the examples for secant and tangent, we'll see that the process for cosecant and cotangent is the exact same. Even though the textbook, to my knowledge, doesn't actually have a breakdown of those, I've sort of copied the procedure for secants and tangents, and when we get there, we can just cross out secants and tangents and replace them with cosecants and cotangents. But since we've talked about neither, maybe wait till we do that and then try that again.
My math lab explained it a little bit.
Oh yeah, what was there? Dare we? Yeah, so it's sort of the same process. So we've got even secant. We're going to break off secant squared or cosecant squared. Yeah, it's the same process for secants and tangents. Yeah. Any other homework questions? All right, we were then looking in A3 at trig integrals, specifically just powers of sines and cosines at this point. And our example here, when number 9 was cosine cubed of 7x, and then sine to the negative 2 of 7x. And so we said, since cosine was odd, we're going to split off a cosine. If it were cosine to the negative 2 sine cubed, sine is odd, we would split sine off. Okay. So with combinations of sines and cosines, even if the sine and cosine are by themselves and they're to the odd power, that's the technique. You always split off an odd power of sine or cosine. Put it with your differential, and that lets you know what your du is. So that lets you know what your u substitution is. Okay, so our u was sine 7x, then our du is cosine 7x times 7. And we don't have a 7 in our integral, so we can either multiply all of this by 7 and then divide by 1/7, kind of how we do when something's in log form, or if you're more accustomed to doing this, that's fine too. All right. So again, I just want to remind you, the things that you split off here in this section should indicate to you what your u substitution is by implication. The things we split off and put with the differential, the dx, the dv, whatever, those are giving us clues as to what our substitution should be. Okay, and so we've got this accounted for. This is our 1/7 du. We've got sine to the negative 2 of 7x. That's our u. We need to take care of the cosine squared of 7x in terms of our u substitution sine. So we're gonna rewrite cosine squared of 7x as 1 minus sine squared of 7x. So we can then u substitute for that expression. All right. So then so our integral turns into 1 minus u squared Sine to the negative 2 becomes u to the negative 2. And our cosine 7x dx is now 1/7 du. So wherever you want to put that 1/7. So again, with u substitution, you've got a polynomial in terms of u. We actually just want to multiply that out. And then integrate the powers of u. So u to the negative 2 minus 1 du. So we have then 1/7, we have u to the negative 1 over negative 1, or negative 1 u to the negative 1 minus u. We'll get a constant here. I'll call it constant 1, C1. And then we can resubstitute. U was sine of 7x. We have 1/7 negative sine of 7x. Now keep in mind it was u to the negative 1. So however you like to write those, but this is sine of 7x to the negative 1. So at this point, don't get that confused with the inverse sine. It's the sine of all of that to the negative 1. It's the reciprocal of sine 7x, not arc sine. Minus u plus that first constant. So, I mean, we could leave it out like that, or we could just multiply the 1/7 in. It doesn't really matter at this point. So this sine of 7x to the negative 1, we can call that, like we said, the reciprocal of sine. So we could write it like it is, or we could call that cosecant of 7x. Minus our sine of 7x here. 1/7 rather. Sine of 7x. And then that constant number 1 multiplied by 1/7 will just be another constant. So we'll just call that capital C. I mean, I think really either one is fine. But we'll go with this one here. Okay. So the processes involving sines and cosines, just really the main thing is look for either one that's to an odd power and split that off. Doesn't matter what the other sine or cosine function is as far as the power goes. If it's a even power of sine or cosine, or both, you've got to use the what they refer to as the power reduction identities that we mentioned here. So those two were for handling even powers of sine, cosine. Does anyone have any questions on sine, cosine stuff? We're gonna. So here are some reduction formulas for powers of these trig functions. There isn't really any need to know this either, unless you just want to. There is actually a procedure referred to in here that does say, if you have this kind of scenario, then do this, and then refer back to the reduction identities. But for the sake of not having to memorize those types of problems won't be on the test, just so you don't have to memorize these. But in certain situations, it is super helpful to know those. But we just don't encounter those because it's not practical to, in my opinion, to test over those. But just so we see how it works, evaluate tangent cubed, and we would use this formula here, number 3. So we just plug that in with n equal to 3. So at some point, those integrals we looked at on the first page, integral of tangent, integral of secant, cotangent, and cosecant, you need to know those. Those are crucial. Notice this tangent formula does boil down to eventually integrating tangent to the first power. So at some point, you need to know how to integrate tangent or find the antiderivative. Same thing with the secant formula. If you're using that formula, eventually you get to secant to the first. You need to know the antiderivative of that, so forth. All right, so our formula says that the antiderivative of tangent cubed is equal to tangent squared x over 2. So of the 1 less, minus the integral of tangent to the 3 minus 2 power. And notice it says the formula is valid as long as it's not n to the first. As long as we're not trying to use the reduction formula to find the antiderivative of tangent, it works. So here we're stuck unless we remember how to find the antiderivative of tangent, which is honestly something you should know, just like you know sines and cosines. So what was the antiderivative of tangent? No, the derivative of tangent is secant squared.
Natural log of secant.
Natural log of absolute value of secant. That's on page 1. ln absolute secant. So that's our antiderivative. Yeah.
Would we get points if we put plus natural log of cosine?
Yeah, because that's also the same thing. Yeah. We also had negative ln cosine, negative ln absolute cosine for this. So let's go ahead and write that. Or, I don't know where I'll put that. Or we could say it's tangent squared over 2 plus the natural log absolute cosine. So either one of those is fine. So that's utilization of the reduction formula. We could also do that here with number 23, secant cubed. But I'm gonna look at it in another way. So I'm just gonna look at the integral or the antiderivative of secant cubed first, and then we can multiply it by 12. So the reduction formula would be easier, of course, but we're going to break secant cubed up into secant squared times secant. And then with secant squared secant, we're going to use integration by parts. Just so we can see an alternative way. The integration by parts, where we said, logarithms, inverse trig functions, that whole thing, it sort of falls apart here, right? Because you have 2 trig functions. So then the question, I guess, is which one, secant squared or secant, should we allow u to be? Secant squared would be u or dv? dv or u? Mixed feelings on that. Yeah, so that a little bit of background on the LIATE when we say let u equal the leftmost function, that's, on the contrary to that is we should let dv be the biggest part of our integrand that we know how to integrate. Does that make sense? That's sort of the converse of the let u equal the LIATE. So we know how to integrate secant, that's true, but we also know how to integrate secant squared. So since we know how to integrate secant squared, we should let that be our dv. Which means that our u should be secant. And granted, this approach that we're taking is not, I think a lot of things that we do aren't obvious, like why would we do this way? Clearly we can break secant cubed down that way, but I mean, I don't know if that's an obvious thing to do that and then say, hey, I'm going to integrate this by parts, right? Anyhow, derivative of secant. Yeah, secant, tangent, and then the integral of the antiderivative of secant squared. Tangent, because the derivative of tangent is secant squared. All right, so we have that. Let me just write this here. We have that, we'll deal with the 12 in a minute. The integral of secant cubed is secant squared secant. We're going to break that up as u times v, so secant tangent. Minus the integral of v times du. So secant squared tangent sorry, VDU, yeah. My bad, I looked at the wrong thing. Secant tangent squared. So then, I think even at this point, it's like, okay, well, that really wasn't much better. I started with a secant squared and a secant. Now I have a secant and a tangent squared. But it's sort of subtle at this point. If we change the tangent squared using the Pythagorean identity, then let's do that, and hopefully we can see where this is headed. So we have 1 plus tangent squared is secant squared. So secant squared minus 1 is tangent squared. And we just combine what we have there on the integrand. So once we get to that point, is that any better, or is that beneficial? Yeah, so we notice that this is what our original antiderivative turned into, right? But we notice that we have another one of those here with this one. So it's kind of like the e to the x cosine x problem. We ended up getting into this loop with integration by parts. We said if we stopped when we had the same integral, then we could just solve for that integral. So that's what we'll do here. We have this one, we're going to add to both sides. So then we have two of these secant cubed antiderivatives. And then we have the minus secant. Left over. Is everybody okay with that? Any questions? All right, so what is the antiderivative of secant? Right, natural log of the absolute value of secant plus tangent. We're kind of being sloppy with these constants, but the point is now I have two of these secant cubed equaling this. That means the antiderivative of secant cubed is just 1/2 times all of that. Whatever, we'll have a constant over here. So even if you use the reduction formula, you do get down to the secant tangent plus the integral of secant. You need to know how to find the antiderivative of secant.
12.
Yeah, and we had our 12 there originally, but by and large, the antiderivative was the bulk of the work. So if that's one of that, then 12 times secant cubed is 12 times that other side too, or 6 secant tangent. What's that stuff? So sometimes there's more than one way around it. Honestly, the reduction formula would have been easier, but I think it's worthwhile to just look at other methods that do work. Okay. Any questions on that example? So with that, we had secants and tangents. Now we'll talk about how to handle integrals that involve tangents, secants, and powers of tangents and secants. So we've got tangent to the m, secant to the n power. The first technique is if n is even. If we have a secant is even. So if secant is even, we can split off a secant squared. So it's just like, it's very analogous to the sine cosine stuff. Secant is even, we split off a secant squared, write the remaining powers in terms of tangent, and use the u substitution, u is equal to tangent. So again, think about if we're splitting off a secant squared and putting it with our differential, then secant squared dx, right? Then we think about, okay, well that's du, then what does u have to be? It has to be tangent, so that when we take the derivative of tangent, we get secant squared. So that implies that du is secant squared. And that's what we split off. We split off as secant squared. So very comparable to sine cosine stuff. If, on the other hand, tangent is odd, odd power of tangent. We split off a secant tangent and let u equal secant. The remaining even powers of tangent is rewritten in terms of secant, again, using the Pythagorean identities. So those are the ones that we deal with. If tangent is even and secant is odd, then it says rewrite the even powers of tangent in terms of secant to produce a polynomial of secant, and then apply reduction formula 4 to each term. So we're not going to deal with those just because it involves the reduction formula, and I don't know that it's necessary to remember that. So really, we've just got one example of this. We can do two ways. So if we want to evaluate the antiderivative of tangent cubed secant to the fourth, notice that fits either one of those. So we'll actually look at this both ways, where if we look at it as, well, secant is even, I'm going to take one approach. Or I could say, since tangent's odd, let me take the other approach. So we'll look at both. Yeah, all right. So if we follow the procedure there, if secant is even, we're going to split off a secant squared. So we have the integral of tangent cubed times secant squared times secant squared x dx. So the thing we split off, we put with our differential, lets us know what our u substitution should be. So we should let u equal tangent, that way du is secant squared. All right, so then our du accounts for this here. Our u substitution accounts for this term here. We just need to take secant squared and rewrite it in terms of the Pythagorean identity. So this is 1 plus tangent squared. And then that way we can account for everything in our integrand based off of our substitution. Let's see, what does that give us? We have u cubed times 1 plus tangent squared, which was u squared. And then secant squared dx was our du. All right, so then we get another polynomial in terms of u, integrate powers of u, just like the other ones have been. So you do have to remember these procedures. So one of these, a couple of these show up on the exam. You need to know like what procedure to use, right? So you do need to know those procedures. Okay, so it's pretty straightforward from here. And then resubstitute. We have tangent to the 4th over 4 plus tangent to the 6th over 6 plus c. So that's one way we could approach that. We saw secant was an even power, so we can split off a secant squared. The other way is to view it through the lens that tangent is odd, which we'll do next. Does anyone have any questions about that? Again, all of these are use substitutions in disguise. You just gotta know what to split off. That's really what this section boils down to. Okay, the other approach is when tangent is odd. Yeah, was that, that's right, oops. That's right. Okay, so tangent cubed secant to the fourth. If tangent is odd, we can split off a secant tangent. We split off a secant tangent when tangent's odd. And then our u substitution here is what?
Secant.
U equals to secant, yeah. So u equals secant du is secant tangent. Which takes care of that. Our u being secant takes care of that. We just need to express tangent squared in terms of secant. So that's secant squared minus 1. The antiderivative of u squared minus 1. Secant cubed is just u cubed. And secant tangent dx was du. That's u to the fifth minus u cubed du. So I mean, you know, we ended up with similar powers here, but our u's are completely different. But we see both of these methods work, even though we have what appears, I mean, on the surface anyways, two totally different functions or two totally different antiderivatives. But the way we could reconcile that is we take the derivative of our antiderivative. We should be able to simplify those to tangent cubed secant to the fourth. That's the idea. So either one as an antiderivative is correct. It's a matter of which method you chose to do. If tangent were even, sorry, if it were like tangent to the -3 power, right, we would see, well, secant is even, so that's the process I want to take. Secant's even, split off a secant squared. So any questions on either of those two? All right then, the process for the strategy for cotangents and cosecants is identical to the process we just looked at with tangents and secants. So I couldn't find anything in the book just to paste in here, so it's, I don't know, it's a bit janky, but everywhere you see tangent, you can just put cotangent. Just didn't want to type all that. Hindsight, I should. Same exact process, though. Did I get them all? Okay, and replace secant with cosecant. But again, these here we don't see for reduction formulas. So if you see like both of them are even, right? If both powers of tangent, secant, or cotangent and cosecant are even, then the one you're defaulting to is focusing on the fact that secant or cosecant is even and using that process. If both of them are odd, then we go to the fact that a tangent or cotangent is odd, so then split off a tangent secant or a cotangent cosecant. Does that make sense? It's not sort of like all or nothing. Okay, so if there aren't any other questions, then we'll leave that section there and move on to 8.4. Okay, all right, 8.4 is another integration technique called trigonometric substitution, or trig sub. So instead of allowing u to be some part of the integrand that's already there, trigonometric substitutions are just that. Some part of the integrand that's there, we let equal a trig function instead. So before we'll talk about why we would, or ask the question why we would want to do that. But the idea of this reference triangle might seem a little bit trivial. But the idea of the reference triangle is crucial to the process of trig substitution. So we need to remember our ratios here. Opposite, hypotenuse, adjacent, that kind of stuff. So sine was defined as what ratio? Opposite over hypotenuse was this here, opposite over hypotenuse, which means cosecant, the reciprocal, is the hypotenuse over the opposite. Cosine was the adjacent side over the hypotenuse, which means secant, the reciprocal, is the hypotenuse over adjacent. And tangent was the side opposite over the side adjacent, which means the reciprocal, cotangent, adjacent over opposite. So we need to know those. Hopefully you haven't forgotten those. And sort of how it shows up in trig substitution, for instance, is we're given the fact that sine theta is x over 8, and it says draw a triangle to determine the value of cosine theta, assuming that theta is in between 0 and pi over 2. I'm going to try this. So we'll call that theta. And we're given the fact that sine of theta is x over 8. So the opposite side over the hypotenuse. Sine is x over 8. And then it asks us to find or determine what is the cosine of theta. Well, cosine of theta is, we need this side right here. We need the adjacent side. So what is this adjacent side's length?
Square root of 5, 6.
Do what?
Square root of 8 squared minus x squared.
Yeah, square root of 8 squared minus x squared. So from the Pythagorean theorem, that side is root 64 minus x squared. So cosine was defined as the adjacent over the hypotenuse. So our adjacent side over the hypotenuse. All right. So that's really how the reciprocal definitions of our trig functions show up in practice, and we'll see once we actually get into trig substitution. Every trig sub problem involves drawing a triangle like this and determining the sides. Without it, you can't go from your substitution that involved theta back to the variable that you started with, which is x or y or whatever. So basically, the idea of this exercise is this lets us convert basically from thetas to x's. Just like when we made a u substitution, at some point you had to make the resubstitution for x. So you had to go back from u's to x's. With trig subs, at some point you have to go back from thetas to your x's, and that's what those reference triangles let us do. So really, why trig sub? Why on earth would we want to substitute a trig function in for x? Seems like it would complicate things as opposed to make it easier. In most cases, I suppose that is true. But we're specifically focusing on a certain type of function. And the types of functions or expressions that show up when we utilize trig substitutions are the sum or difference of squares. So when working with the sum or difference, like x squared minus a squared, x squared plus a squared, and a squared minus x squared. The sums and differences of squares. So in the context of those types of expressions, that's where trig substitution shows up. And so when working with sums and differences of squares, trig substitution allows us to turn these into product or products of squares. So think even with that brief explanation, doesn't really do it justice. So let's just consider looking at an example. Before we actually integrate, we'll just look at an example algebraically before we actually turn to the antiderivatives. Okay, so consider I'll just say y. So consider the function 1 minus x, the root of 1 minus x squared. So if I gave you the problem to find the antiderivative of the square root of 1 minus x squared, that would be rather difficult to do, right? And how would you do that? You can't, it's not a u substitution because the derivative's not out. It's not an inverse sine integral, right? So then we see, okay, well, the trig substitution allows me to take that difference of squares and turn it into a product of squares. So instead of a difference of squares that I can't take the square root of, if I can put a product in there, then I can take the square root of a product, right? So, you know, like a squared times b squared, we can take the square root of that. So algebraically, what this allows us to do is we can take the square root of 1 minus x squared, and I can say let, and as far as the substitutions for trig functions, it hinges off the Pythagorean identities. So we're going to let here, we're going to let x equal to the sine of theta. Because 1 minus sine squared turns into cosine squared, right? Or you could let x equal cosine squared because 1 minus cosine squared is sine squared. So we have the square root of 1 minus sine squared. And we know 1 minus sine squared is cosine squared. So that's cosine squared. And what's the square root of cosine squared? Cosine. Technically it's absolute value of cosine, but we'll address that in a minute. Okay. So algebraically, we can, if we make a substitution, sine theta equals x, I can turn the difference of squares under the radical into a square and take its square root. So instead of saying what's the antiderivative of 1 minus x squared, with a trig substitution, I can work this into my antiderivative, and that's much easier to work with. All right, so that's a simple example to illustrate, you know, how trig substitution helps us. Okay, does anyone have any questions on that? Naturally, we wouldn't just make the straight substitution that all of this root is cosine theta, right? So we couldn't just say that all of this algebraically we saw is, based on our substitution, it's cosine theta. You have to account for the differential too, right? So we have to involve the derivative as well. Not the derivative of cosine, but the derivative of our original substitution. Because if we say, all right, we're going to let x equal sine theta, to account for dx, we have to take the derivative. So then what happens is that this becomes the square root of 1 minus x squared became cosine theta, and then the dx, as we saw here, the dx is cosine theta d theta. But still, we don't know how to find the antiderivative of the root 1 minus x squared, but we can find the antiderivative of cosine squared. So once we find the antiderivative of cosine squared in terms of theta, we have to resubstitute x, and then that's where that triangle comes in. So it's a lengthy process, but like I said, antiderivatives are difficult. So we'll look at a specific example in a minute. The three cases that we saw come from the difference of squares and the sum of squares in the middle. So our scenarios here, we have our thetas. This one's going to be a side length here, x. This one, the base, will be a, other length x. And then third one, hypotenuse x, base a. So the algebraic way that we're going to do this in class is different than how your textbook does it. I'll try to make mention of that in case you do like that method better. It's really 6 in one, half a dozen in the other. Do you want to kind of simplify it first, or do you want to simplify it later, is kind of the difference. So your textbooks use these a squared minus x squared, a squared plus x squared, and x squared minus a squared. And then the textbook says identify which form you're dealing with. And then which form you're dealing with, again, you want to think about those squares relating back to the Pythagorean identities, so that you can make the appropriate substitution with either of these three. And then it says, we're going to choose the correct substitution, either a sine theta, a tangent theta, or a secant theta for x, depending on which one we have. So for a sine theta, that's the scenario that we started with, a squared minus x squared. So think about the Pythagorean identity, 1 minus sine squared gives us cosine squared. 1 plus tangent squared gives us secant squared, and secant squared minus 1 gives us tangent squared. So I know it's weird to think about the a's and the x's as one and a trig function, but that's exactly what they're based off of. Okay, so the a tangent theta comes from the sum of squares, and a secant theta comes from x squared minus a squared. Make the substitution, simplify, integrate techniques from, this should be 8.2. Integrate, use techniques from 8.2, which was integration by parts, and even techniques from 8.3 show up here as well. If you're going to follow that procedure. That's from the textbook. So the way we're going to look at it in class is we're going to work on simplifying the a squared minus x squared plus, or a squared plus x squared minus a squared. Those three situations we're going to simplify before we make our substitution. Your textbook just says based on this situation, 1, 2, or 3, you automatically default and make this substitution. Okay. So the way we're simplifying these things is we're going to factor out the a squared from both of these terms. So we're going to have a squared times 1 minus x squared over a squared which is a squared times the quantity 1 minus x over a quantity squared. And so that way, maybe it's a little bit more characteristic of how you see the Pythagorean identities. Let's see, 1 minus something squared needs to turn into a square. Hopefully you think of sine. 1 minus sine squared is cosine squared, right? Same thing with the other two. factor out the a squared. Plus x over a quantity squared, and then when you think about 1 plus a trig function squared, hopefully you're thinking 1 plus tangent squared. So that's our substitution for tangent. And we write these here too. I'm kind of working in reverse, but 1 plus tangent squared, that whole thing in the brackets is going to turn into secant squared. 1 minus sine squared, so this tells us that our substitution x over a should be sine theta. Is everyone all right with that? I'm not quite sure that reasoning makes sense, but they are based on the Pythagorean identities. And then here again, we're factoring out the a squared. So we have x over a quantity squared minus 1. So here we think secant squared minus 1 turns all of that into tangent squared. So x over a secant theta. And just be careful when you say like x over a is equal to secant, tangent, or sine, make sure you're using a different variable. I see a lot of people say x over a is equal to tangent of x, for instance. It's just like a u substitution. You've got to introduce a new variable. Okay, so notice that, you know, if we have the a squared minus x squared, and we say that we're going to let x over a be sine theta, that's exactly what we have here from the textbook. If we have a squared minus x squared, then they're going to say let x equal to a sine theta. But we just know algebraically if x equals a sine theta, then x over a up here, x over a is sine theta, right? So it's really one and the same thing. Okay. So let's actually see how that works then. You know, for ones like this, or the ones that we looked at originally, the square root of 1 minus x squared, if they had bounds on them, like, you know, going from, I don't know, but if we had bounds here, if that's a definite integral, then that becomes a much easier thing to answer, right? So we don't even need to find the antiderivative of that, right? So we recognize the square root of 64 minus x squared is what? So what if this were our function? Doesn't that mean that y squared is 64 minus x squared? And doesn't that mean x squared plus y squared equals 64? So what is that? It's a circle centered at 0, 0 with a radius of 8, right? But we have the positive root, so it's half of the circle, the top half of the circle, when y is positive. Oops. So if this were, let's say this were, if it says find the integral from 0 to 8 of this function, then we say, well, that's just the area of a quarter of a circle. So we can say that area with this integral is pi r squared divided by 4, right? So it sort of takes the mysticism out of it if we can look at it geometrically. But that's not the problem we have. The problem we have is just finding the antiderivative of that. So when we look at that and we see, well, there's no u substitution available, right? There's not a product of two functions of x, so it wouldn't make sense to do integration by parts here. I do have the sum or difference of squares, so that should automatically trigger in your mind, I should probably use a trig substitution here. So before we actually do that, again, the text, if you're going to use this method, the text says we're going to let we're gonna let x equal to, go back here just so we can reference this. We have the blue situation here where we have 64 minus x squared. So the textbook is gonna say, let x equal to 8 sine theta. And maybe we can look at that in a minute, but the way we're gonna do this, or I'm gonna do this anyways, is we're gonna say that that original integral is the square root. I'm factoring out the a squared like we did in all of the other ones, so I'm gonna factor out the 64. So I have 64 times 1 minus x squared over 64 dx. And so I have the square root of 64 I can take out. That's just going to give me the 8. And then 1 minus the square root, rather, of 1 minus the quantity x over 8 squared. So that's kind of the first step we're going to take. And then based on the scenario that we have inside the root, it's 1 minus square. So you think of which trig identity or Pythagorean identity would help there. Is 1 minus tangent squared, secant squared. You got to remember those. 1 minus sine squared is cosine squared. So if I can turn all of this stuff, I can turn all of this into a square, that's going to get rid of the square root. Okay. So my substitution here is I'm going to let x over 8 equal to sine theta. But I also have to account for the differential, the dx. So if x over 8 is sine theta, then what is dx equal to? Excuse me. 8 cosine theta, right? Because if x over 8 is sine theta, then x is just 8 sine theta. So dx, 8 times the derivative of sine theta. So 8 cosine theta d theta. Okay, questions on what we've done or why we've done it? So we're going to substitute into our integral. We had 8 antiderivative square root of 1 minus x over 8 squared, which we said was sine. Our dx is replaced by 8 cosine theta, it's d theta. So we have 64. Again, we'll call 1 minus sine squared, cosine squared. So we have 64 times the antiderivative of cosine, or cosine theta, times the other cosine theta d theta. So we have to integrate cosine squared. So, I mean, it's a lot of work, but we did improve our situation. At least we know how to find the antiderivative of cosine squared. Any questions on what we've done? So if you're taking the textbook approach, hopefully this marker will last. And we're just going to let x equal to 8 sine theta, so that this becomes the square root of 64 minus 8 sine theta squared, right? But notice you have to do some simplification in here, right? Because this isn't a direct Pythagorean identity. So from here, what you have to say is, okay, well, that's 64 minus 64 sine squared theta. From here, you have to factor out the 64 and say that's 64 times 1 minus sine squared theta. And so the square root of 64 gives us 8. The square root of this right here, or whatever, this is cosine square root of cosine squared theta. You see, that's exactly what we ended up with, right? So it's the same approach. It's just I guess a slightly different substitution, maybe. I don't know. I don't care which, if you're going to use the textbooks or this, because it's all the same. All right then, so how do we integrate or find the antiderivative of cosine squared? Yeah, you could try it by parts. I think there's an easier way though. Remember this? Power, from AP 3 anyways, they call that the power reduction formula. So we're going to say that 64 times the antiderivative of 1/2 1 plus cosine 2 theta d theta. We have 32 times the antiderivative of 1 plus cosine 2 theta d theta. Y'all with me? So already it's like, well, you know, a simple function that was just the top half of a circle turns out to be pretty hard to do and to find the antiderivative analytically. Because I would say at this stage we're about halfway done. Okay, so then we've got our 32 times theta plus the antiderivative of cosine 2 theta, which is sine 2 theta over 2. You know, and then we'll have some constant that's going to get multiplied by 32. So let's call it constant 1, C1. Okay, cool, we've done the antiderivative. Now we need everything back in terms of x, not theta. So this is where we draw the triangle. And again, this is based, the triangle is based off of your substitution. We're the ones that initially chose to let x over 8 be sine theta. So sine of theta is x over 8, means the opposite is x, the hypotenuse is 8. What's then the base of the triangle? Yeah, it's always, see, it's always the thing that appears that we're substituting initially for. Okay. Here that doesn't help us all that much, right? Because we need to know what theta is. I don't care what sine of theta is or cosine of theta is. I need to resubstitute for theta. What is theta? If the triangle really doesn't help us that much. Kind of does. Yeah. Right. That's right. Yeah, why wouldn't it be right? If we said x over 8 is sine theta, then isn't theta the inverse sine of x over 8? Yeah, have faith, man. So we'll just say this was based off the fact that sine theta was x over 8, which means that theta is the inverse sine of x over 8. So, all right, cool. We have a x representation for that theta. How about sine of 2 theta? We only have a representation for theta in this triangle here. Sorry? Could we couldn't just multiply it by 2, because that would give us 2 sine theta.
Double angle.
Yeah, the double angle identity. Sine of 2 theta is actually, yeah. Now we have everything in terms of theta. So really that's kind of the first step here. I want everything in terms of a single theta, not 2 theta. So I'm going to say that sine of 2 theta. I'm going to say that this is actually 2 sine theta cosine theta all over 2 plus that constant. Okay. We've accounted for theta. Now we can account for the sine times the cosine. So we already know what sine is. Sine of theta is just x over 8. What's the cosine of theta? Yeah. So theta was inverse sine of x over 8. Sine plus sine times cosine. Sine was x over 8 times cosine, square root of 64 minus x squared all over 8. And then still plus this constant floating around. So we have 32 inverse sine of x over 8. 32 over 64. So we have x times the square root of 64 minus x squared over 2 plus some other constant. So that's our antiderivative. So questions on that?
So when are we actually going to use this in like real life?
Yeah. Yeah, the crux of every math teach's
I have
existence.
to. Like, what is that?
Well,
It's when you gotta find.
antiderivative, like antiderivatives aren't terribly useful. It's always the definite integrals that give us the physical applications.
Oh, okay, yeah, because it needs to balance.
Yeah, right. So
So say we do have some balance where we get some stuff like this, what's it going to solve?
I don't know. What we've seen, anyways, for us is that integrals can represent distance traveled, displacement, volume, area, surface area,
So this just goes all back into that.
work, force. Yeah, could be any of that.
But like in real life, we can just Google it.
Yeah, but like in real life, you're working for an engineering firm. Are they going to want you to do this? No. Right? They're going to say, hey, I have this problem, figure it out. And you're going to go, all right, well, here's my little diagram. This has to be this. Okay, integrate this, type in the computer, enter. Okay, the answer is 34 pi. Cool. Hey, boss, we need a volume of 34 pi. That's how it works.
Great.
So in real life, unless you're just doing this stuff for fun, maybe you won't see this directly, but maybe it lights up new pathways in your brains and different ways to think about something, and that's just cool in and of itself, I think. Not that this is absolutely a perfect, legitimate question. If I didn't teach math, I wouldn't see this. Promise. You just wouldn't deal with it. And honestly, I don't know what engineers do. I've worked with engineers, but to me, it seemed like they were just drawing stuff on their computer in CAD or SolidWorks, and then that program does everything for you. Yeah, so we're like cavemen chipping away at the stone tablet when there's everybody else's writing out here. No, but yeah, it's totally just a mental exercise. Where think of it just as expanding your brain into new realms of possibility. Right. All right. So let's take a break. I didn't realize we kind of went so far off, but yeah, we'll take a break and then have you work this problem when we get back. Right.
Yeah, I don't need this actually. I can use my phone.
Yeah. Yeah.
The first thing is cosine. And the next thing.
It's like, looks like I'm trying to like.
Yeah, but you want a negative. Yeah.
This is what this function is. Looks like an integral kind of.
That's actually true. I'm not gonna lie. Like in the majority of my physics class, the integrals are in
Yeah, because you have this over here.
I actually found out that you don't need to use it.
Yeah.
This is already right for you.
Yeah.
Did end.
Yeah, you don't
Kind of like,
need
like color mode.
Honestly, yeah, that's what I've
It's-
heard. Like, it's not like,
It's not that it didn't work.
It's like similar.
It's just that it didn't give you any information.
I think it's
You already know that 0 is equal to 0. So it's like, all right, well, it did nothing for me. So yeah.
Can we get our exams?
Oh yeah. They're in my office. So
I guess it makes sense.
follow along. Yeah, we looked at it.
Once again, I got the answer.
Yeah.
Because seeking almost the same thing. Yeah, it almost becomes the same thing because
Look at it.
He can do that. I have no idea. Apparently, yes.
So just keep in mind, that is the antiderivative. And notice how it's defined from -8 to 8. Right? We kind of addressed that when we talked about the given function this was a half circle radius of 8, right? So that function is defined from -8 to 8. So when we look at the antiderivative, we see that it's defined from -8 to 8 as well. So it does, the domain of the function reconciles with the domain of the antiderivative just for that piece alone. Anyhow, if y'all are going on to Calc, if anybody goes on to Calc 3, you start to look at double integrals and triple integrals, and those describe, in a lot of instances, they still describe how do we find the mass. But right, Calc 1 and Calc 2 deal with this two-dimensional thing, right? You're living on a piece of paper. In Calc 3, then you step out into the real world. How do we find the mass of a thin bar? Well, we already talked about how to do that, but how do you find the mass of a piece of metal that's bumpy, right? How do you find the mass of that? Or how do you find the center of mass of that? So a lot of like three-dimensional real-world problems can be translated down to the second dimension where things are a little bit easier, right? Even when we talk about a distance, like if I had a distance from here to some other location, I can always draw a right triangle and find some other distance. Even though that distance is really happening in real time in three-dimensional space, we still can talk about the two-dimensional space that it occupies, right? So, I don't know. Math is really complex. At some point, if you go on far enough in any subject, I promise you'll get to the point where it's like, what the heck are we even talking about anymore? Like, that's kind of where I got with math. It's just like, I don't understand what's going on anymore.
When did that happen to you?
I hope y'all don't feel like that in Calc 2, but anyhow, give this integral a shot.
This is the same thing. Except for it's outside.
It's still signed, right? Yeah, it's one round.
Wait, so. Is it cussing?
It's just a squared minus x squared.
Yeah, but it's 1 over that.
Yeah, but what if you just equals that?
Well, I don't think that works.
Because then you get 1 over cosine of
And then that's where I know
that.
there is a parenthesis.
No, wait.
Then that's secant.
But you start with something.
But you start second, so it's like cosine.
No.
Whatever. I totally agree. I'm not gonna write that out. It was like about 20 lessons. I was like, why don't we not just do
Just one. And then just do one. I got you.
I'm waiting.
Cosine squared. Comes cosine of cosine. Oh, you go? Yeah.
What?
The underside.
Yeah, I think so. As far as what it turns into, I believe it is.
I always wondered, when do you use I again? Like learn it in like algebra 2?
Oh, yeah.
Yeah.
Never use it.
You would see it again in like if you took like a electrical engineering class, whatever those are. You would see that. They use I. They call it J. Or if you took any complex analysis class, which is a higher level math class, it's all about working with complex numbers. Like you can do calculus and complex numbers. That's pretty crazy. But it's also cool. It's like the coolest math class I've ever had. So a lot of these things like this can be translated into the complex sense, and there's methods for like complex variables that makes doing stuff like this a lot easier. So yeah, it's pretty powerful stuff.
That's divided by that, with data.
Well, it's one, right?
Well, okay.
Yeah. Yeah. Yeah.
You guys have
I took it 1 6 hours. That's why I took a 6 hour when I had it this time.
Yeah, how did I get 36?
It's not endless.
Okay, you do it.
That's DJ.
Just get a bunch of steps.
Oh, it's just a
One detail.
Yeah.
Yeah, that's what I was
It's just missing.
So it's just becomes stable. Because it's just never written for this one. Also,
Yeah.
Then we can pull 81 out.
Because that's where X is.
So you can pull 81 and then become 1 over 81.
X.
X, right? Square.
Sure, 36.
Yeah, so.
This is 6 cosine.
Yeah, so you call this 6 and it cancels with
Should end
one.
up being cosine over cosine.
Then you get one.
Yeah, so it's,
You're playing calculator.
Yeah, so answer. So that's the answer. Maybe all but one person recognized that as an inverse sine integral or antiderivative. You should recognize that as inverse sine, but I think what you've done through trig substitution is shown yourself that if you happen to forget that, now you have another fallback, right? You can get there through trig substitution. So we factor out the 36 and then take the square root of that. Keep in mind it's in the denominator, so we take out that 1 over 6. So 1 minus x over 6 quantity squared. I'm going to let u equal to x over, or sorry, x over 6 equal to sine theta or whatever. So, you know, just keep in mind that our substitution means that 6 sine theta is x. That's kind of the textbook's approach. Sorry, x dx rather 6 cosine theta d theta. So there's our substitution. The 6's cancel out. Okay, so we end up with that cosine theta on top still. So there's a minor but important technicality that we're skirting when we say that this is just cosine theta d theta all over the square root of cosine squared, and we're just calling that cosine theta. Yeah, we alluded to that earlier. When you take the square root of a quantity squared, it's the absolute value of that quantity. So I'll go back to I posted something from the textbook into our notes, and that we'll talk about. So that's the long way. Did anyone have any questions on that? All right, then let me go back. I put it on this page. So here again is the integral contains one of these three things, then here's our substitution. But notice here what they also give us is they give us this where theta is with each substitution. So our substitution, we had sine theta, and so we'll just say x over a, the inverse sine of that is theta. Remember that so the theta between negative pi over 2 and pi over 2 from this one, That's just coming from the fact that our substitution involves sine theta, and the inverse sine of something is theta, right? So the inverse sine always outputs theta. The inverse sine's range is negative pi over 2 to pi over 2, right? So that's where those come from, or the range of the inverse tangent, the range is from negative pi over 2 to pi over 2. The range of inverse secant gives us where theta has to be in that substitution. So just in brief, these problems are set up so you don't have to worry about the absolute value, because then that's a much more difficult problem. But if we go here and we say that our substitution was this right here, which means that, again, that theta is the inverse sine of x over 6. And theta is in between the range of inverse sine from negative pi over 2 to pi over 2. Well, if theta is in between negative pi over 2 and pi over 2, cosine is always positive. So that's why we don't have to ensure the absolute value around this. So I'll just put this here in our notes. It's not really something, it's something you should be aware of, but it's not something that shows up in practice. So no absolute, I'll just abbreviate, no absolute value is needed. All right. So that's how we skirt that issue. So I want to skip ahead a little bit. So for instance, this integral here, where we have x squared minus 81, they tell us that x is larger than 9. So that's example 5. So they give us the fact that x is larger than 9, which plays into this one here. So if x is larger than or equal to a, which is 9, if x is larger than or equal to 9, then theta is in this interval when we're dealing with the secant. And so the square root there is always positive. The square root of that function squared is always positive. Okay. That's why in example 5, x is larger than 9, just so we're dealing with the positive aspect and not positive and negative. So like I said, these problems are constructed where we don't have to think about that technically anyways. Okay. So 18 over 81x squared plus 1 squared. This time we have our square plus 1, right? So we don't want to think, this isn't sine, because sine squared plus 1 isn't another square. This here is tangent squared plus 1 is equal to secant squared, right? So however you want to remember that, I think some people just memorize the form, but it is based on identities. So let's write 81x squared, with all of this stuff on the bottom squared. We'll write 81x squared as 9x quantity squared plus 1. So we see though there's not a presence of the square root on the 81x squared plus 1, but we still notice that a u substitution wouldn't work and integration by parts wouldn't work. We don't have two functions of x multiplied together. So then we might notice, well, I have the sum of squares. Let me try trig substitution. So we're going to let 9x equal to tangent of theta. And then dx is what? Is what? Secant squared theta for tangent, yeah. Yeah. But if x is tangent, then sorry, 9x is tangent, then x over x is equal to tangent over 9, right? So this is over 9 as well. Okay. So then let's see what happens when we rewrite this. We're 18 integral dx 1 over 9 secant squared theta d theta over this thing squared. So that turns into tangent theta plus 1, tangent theta squared rather. Okay. So that looks weird. Okay, 1/9 in the 18. 2 integral. We've got a secant squared theta d theta. Tangent squared plus 1 is also secant squared. Squared. I need more space. All right. So, everybody all right with that, where we're at? Any questions? So you got secant squared over secant to the 4th. What's the antiderivative of 1 over secant squared? Yeah, it was 1 over secant squared is just cosine squared. And there's our friend again. Sine and cosine squared are really common antiderivatives. We have power reduction, 1/2 the 2. End up with this. We did in that other one. So we end up with theta plus sine 2 theta over 2 plus c. So there we see the sine 2 theta again. Same thing if you had a sine squared, you're going to end up with a negative sine 2 theta. We always want to change that, in this setting anyways, we always want to change the sine 2 theta into sine theta times cosine times 2. So that'll cancel with the 2 on bottom. No. Oh yeah, it did, because we had the 1/2 times this, right? Yeah. So that 1/2 canceled with this 1/2, or with this 2 rather. And then this 2 cancels with this 2. So back to x, we need a triangle. Based on our original substitution, that tangent of theta was 9x. So the opposite side is 9x. The adjacent side is 1, because that's 9x over 1 is 9x. Makes our hypotenuse what? 9x squared plus 1, or 81x squared plus 1. Okay, so what is theta?
Inverse tangent of 9x.
Yep, inverse tangent of 9x. Because 9x was tangent theta plus sine of theta, opposite over hypotenuse. 9x over the root. Sine x times cosine x. 1 over the root. Plus c. See, I'll write this here. Okay, we can simplify our radicals. That's pretty much it. So inverse tangent of 9x plus 9x over 81x squared plus 1 plus c. Any questions on that?
Did you go over that after you got to the triangle?
From theta sine cosine theta, from there? You okay with the triangle then?
Well, yeah, how do you do the one?
The 1, because tangent is 9x over 1. So the opposite, this is the opposite over the adjacent. Okay. And since tangent of theta was 9x, we just solved that for theta. Just take the inverse tangent of both sides to get theta, this here. And then sine of that angle was just the opposite over the hypotenuse of the triangle. Cosine adjacent over hypotenuse. All right. Any other questions? Huh? Not on me, nope.
Can you bring some for class?
Yeah, yeah.
Test days, please.
So yeah, the antiderivatives versus the definite integrals. Here I would just recommend that you find the antiderivative, resubstitute in terms of x, and then plug the bounds in. If you want to convert your x's into thetas based off of your substitution, and then just work with the integral involving theta. Let's see what we end up with. Yeah, I mean you could totally do that if you want. I didn't actually do that, but. So here, what's going to be our substitution? Sine, tangent, or secant? Yeah, tangent. We have the sum of squares, tangent. So I'll just say this first. Find just the antiderivative. So we'll just kind of configure that how we've configured the other ones. factor the 16 out. So keep in mind, again, that's in the denominator, the square root of 16. Take that out. There's 1/4. And then we have the square root of x over 4, quantity squared, plus 1. So we're going to allow x over 4 to be tangent. Dx then is 4 secant squared theta d theta. So we've got our 1/4 integral dx on top. We have 4 secant squared theta d theta. The square root of x over 4, which is tangent squared plus 1. The 4s and the 1/4 cancel out. So we have the antiderivative secant squared theta on top, and then the square root of secant squared theta. So we have, what, secant squared over secant which is just secant. So what's the antiderivative of secant?
Natural log of secant squared plus tangent squared.
No, not the, close, they're not squared though.
Tangent, theta, sorry.
Yeah, ln secant plus tangent. Okay. Resubstitute. Already forgot. X over 4 is tangent. X over 4. So we already have x over 4 as tangent theta. That was our original substitution for the second term. What's secant of theta, though, in terms of x? What is it?
Hypotenuse over 4.
Yeah, hypotenuse over 4. Tangent was x over 4. So this is going into a definite integral, which is why I'm not putting the plus c. Remember, the c could be anything in the definite integral because it always just subtracts out to 0. All right, so that is the antiderivative of the function in terms of x. So we can then evaluate from 0 to 1. We could also simplify this expression for ln of absolute value. We could simplify that a little bit more just to make evaluation a little bit easier. So it's fine if you just want to leave it like that and then plug the bounds in from 0 to 1. That's totally acceptable. I'm gonna write this up here once we're done. So this is okay, but we could simplify. A bit more. Not, I guess what follows isn't absolutely necessary to do. But we can write this as the natural log of the absolute value of the square root of x squared plus 16 plus x all over 4. And then using properties of logarithms, when we have the logarithm of a quotient, you can break that up as the logarithm of the numerator minus the log of the denominator. So that's how we'll split that up. Log of the numerator minus the log of the denominator. We don't really need the absolute value here. But what we'll see is we don't need the negative ln 4 there at all, right? Because isn't that just another constant? It's just another constant in terms of definite integrals. We've already seen what happens to constants. They just go away, right? Yeah, we have bounds on it, but it's constant, so it doesn't matter. The x's don't get plugged into negative ln 4, right? So we have f of b with the negative ln 4 minus f of a with the negative ln 4, negative ln 4 minus negative ln 4. They're gone. So constant, which means that is for a definite integral, constants are not needed for a definite integral. That's the key operating word there, phrase there. So if we wanted to, we could just say that this is ln absolute square root of x squared plus 16 plus x. And then we could, quote unquote, simplify that a little more as well and say, also, since x is in this, have y'all seen the symbol that for, if you've looked in the textbook, you might have seen this symbol. Kind of looks like an E. That's the same thing. X is in the interval 0 to 1. It's more the technical way to say that. It really means X is an element of that set, but it means X is in that set. We don't need absolute value since X is from 0 to 1. Absolute value. The square root's always positive. Something positive added to anything between 0 and 1, including, is always positive as well. So I don't know, maybe we're just trying to be clever and a little bit lazy and not evaluate all of that stuff from 0 to 1. We could just say it's this right here, evaluated from 0 to 1. And honestly, to be technical about it, we should have had the bounds kind of floating around, but we're sort of bypassing that technicality, saying, well, we know we're going to end up doing an antiderivative or a definite integral. Here, we were just trying to figure out what the antiderivative was. So then, from here, we'll say that the integral from 0 to 1 that is equal to the ln of the square root of x squared plus 16 plus x evaluated from 0 to 1. So just leave our answer exact because it's really not a pretty number. We have the ln of all of that is evaluated at 1, so we have the square root of 17 plus 1. Remember, that's the ln of that quantity minus f of a, so square root of 16 ln 4. So that's our answer.
But from the ln of 4 from before, does it not matter?
Yeah, no relation. If we had that other ln4 here, then like I said, we would have all of this stuff minus ln4, and then we would have minus this stuff minus ln4 as well. So again, that L minus ln4 and that ln4 would cancel out.
On the test, are you gonna want us to like put that in a calculator and figure that out?
I would just leave it exact. It's fine. Yeah. Okay. Let me know if you have any questions on this stuff. Be around. Have a good week.